Ugh. I'm going to talk about significant figures and just sort of lay it out there. I hate significant figures. They're a pain in the butt. However, you should have some exposure to them. How many of you have dealt with significant figures before? Okay, all but one. Or two. All but one. All right. I'm going to go through it relatively quickly. In terms of significant figures, why am I going through it when I don't like them? Well, as I said, you should have some exposure to them. I am requiring significant figures for the first lab. After that, I don't care. So first lab, significant figures, count. After that, just go crazy. The point of significant figures is to give some indication of how important each number is. Is that a true statement?
Not when dealing with significant figures.
When is it true? Besides the negative. In what class would this be true?
Math.
Yeah. And again, this is not math class. The difference between these two numbers is that this is rounded off to the nearest one. This represents some number from 0.5 to 1.5. This number represents some number from 1.0005 to 1.0015. Significant figures tells you how precise the answer actually is. To determine the number of significant figures, well, any non-zero number is significant. Check. And then it breaks down to, make sure I'm not going to leave something off here. Left of decimal point, right of decimal point, two different rules. And I guess in between. So zeros in between non-zeros are significant. And then comes down to whether you're left of the decimal or right of the decimal. If you're to the right of the decimal, trailing zeros, significant. Left of the decimal,
Not significant until there's an actual, unless there's trailing zeros after the decimal.
only if decimal point exists. So if I have 5,000 with a decimal point there, those zeros are significant. Sometimes that will be written as 5,000 with that zero underlined to emphasize that is significant there. However, 5,000, so probably should change this, zero in between non-zero, zero in between significant digits. So that zero is significant, that 5 is significant because it's non-zero, and so therefore the ones in between count. This has 4 significant figures. This has 4 significant figures, just different notation for the same thing. This has 1. This was rounded off to the nearest thousandth. These were rounded off to the nearest 1. Questions to there? Addition and subtraction. First off, how many significant digits does this number have?
2.
Yeah. These zeros right here are not significant. They're just making sure that this 1 is in the right place. How many significant digits here?
40.
All right. number of significant digits is not as particularly important when you're adding and subtracting. What you care about is what is the precision here. This is to the nearest thousandth. This is to the nearest 10,000th. When you add them, you go to the
10,000.
To the thousand.
thousandth, the one that's less, has less precision to it. If it were the other way around, I just mowed 1,000,000 lawns, and then I mowed one more. That doesn't mean that it really mowed 1,000,001. Depends on if that first number was precise or not. But when you add them, you keep them all there, and then you round off. So that's the answer from a math point of view, but because our significance here, this is the least precise, we round off to that, and so we would write our final answer as 2.45. Recognize, significant figures are about presentation. If I need to use this number for another calculation, I am going to be using that for further calculations. This is just how I present my answer. So this is for presentation. Multiplication and division have the same rule. So that cares about the number of significant figures. So times 0.0016. This has 4 sig figs. This has 2 sig figs. And so if I multiply them, I get something. Someone be kind enough to pull out the calculator and let me know. First give me the full answer, and then we'll write down the presented answer.
So 0.0083888. Yeah, that's the way my calculator set up in the round.
All right.
And there's probably more.
Right, no, but we're off somewhere. Order of magnitude. Is there a times 10 to the something?
It's 0.0, not 2.0.
Yeah, and zero.
Oh, 0, okay, oh, sorry. As when I talk about in one of the videos, my hearing is not great and the math just really add to it. So I apologize. Now, when multiplying and dividing, we care about the number of significant figures. This has only 2 significant figures, so our answer has only 2 significant figures. And so that means we're going to here, so 0.008. 4 is our presented answer. Assuming that for the 11 of you who dealt with it before, it was chemistry? Anyone?
Russell? Yeah, kind of sure.
Yeah, they really care about that a lot more. That's really all I want to say. And I know if you've never seen it before, it's been a while since you've seen it, then this really wasn't much. There's the textbook, and then what I'm also going to do is, and this goes for anything, ask questions. If you start getting into the weeds of the lab and you start getting confused about how many significant figures, just ask. Oh, I do want to talk about exact numbers. There are 100 years in a century. I'm hoping that's not a shock. How many significant figures?
1.
Nope.
Three.
Nope. Austin? That's an exact number. For exact numbers, it is infinite significance. It's not rounded off at all. It's just that we don't feel like writing out every single zero after a decimal point. So for exact numbers, infinite significance. I guess infinite number of significant figures. And if it's like most years, then I'm gonna start getting into the grading, going, man, I really should have spent more time on significant digits because people are messing this up. And then I'll think, well, next year I just won't bother with them. And then I do it again, and it's a vicious cycle.
That means then that 100 years is infinite significant figures?
Right.
Okay.
Any other questions before I start erasing?
So for
Awesome.
the multiplication and division, you just take the lesser sig big.
Yep.
That's what you're rounding to, and then for addition, subtraction, just line up the decimals, and then it's ever shorter, that's what you round to.
Less precise, probably better word.
Less precise, you got it, okay.
And now, everybody's second favorite topic, propagation of error. How many of you dealt with propagation of error before? Editing quadrature?
Yeah.
Was that a sound of joy? Or is that a no? It sounded like it was coming from somewhere over here.
I remember very vaguely on a funny equation, like a Gauss or something like that, I don't recall. A Gauss.
All right, yeah, I think you can tie it all back to the Gaussian stuff, which is basically, I think all statistics ties back to Gaussian somehow. I've tried to come up with a better explanation for why the statistics people do what they do with us. And I get inklings, and then they start throwing in a lot of terminology to make me go, well, I guess that's what I get for not taking a statistics course. Statistics I know I picked up on the streets. Oh, those dang years. All right. So let's say I'm going to do a measurement, and we'll just 5.1, 7.2, 5. So let's say that we are measuring the length of a table. Now, why these are so far off, just cause. And so what I want to figure out is, there's a couple of terminology. Average, I think most of you can handle. Although I did teach one class a number of years ago where someone did ask, how do you do averages? I'm hoping at the calculus level, you guys are good with that. So first off, average. What is the average, the numbers?
All them up, added all together, divided by the number.
All right, and the actual value? Now that was the situation right there. My big emphasis is please answer the question that I asked, and he indeed did. In this case, my reading would have helped. But especially on labs analysis questions, please make sure you answer the questions that I ask and not a question you wish I asked.
5.7.
Exact? Oh, okay. I'll write it out. Standard deviation. What is standard deviation?
I vaguely remember, I can
remember hearing that before.
Like the deviation of the
something
data.
like the summation from,
Right.
I think it's the number of responses, or the number of data, I can't
I
remember.
think how far off each of those answers is from the average, maybe?
Yeah, pretty much. I mean, it's something like that. I don't know if you were just going off the wordplay or
I
whether.
was like going for something like that. Yeah.
Okay.
It kind of came back to me with the two wheels,
And this is why face-to-face works so much better than online. All right, so standard deviation is an indication of how the numbers are spread out. The larger the standard deviation, the greater the spread. Smaller standard deviation, the smaller the spread. Now, most of you have calculators that will do this. I still have had students, even though they have the TI 80 whatevers, which I know can do it, they still want to do it by hand. So we're going to go through this one by hand, just for the fun of it. We're heading towards uncertainty, but standard deviation, you basically find the difference between this and the average. And so we have negative 0.6, 1.5, somebody correct me if I make a mistake here, negative 0.4, 0.4, negative 1.2, negative 2, and 2.5. And you can do a quick check if you're doing this by hand. Is if you add these all up, it should add up to 0. So 0.9, let's cancel out. 0.9, 3. Try that again. So 0.9, 3.4, off somewhere. 2.
Probably because I think there's a lot of decimals after the average, I don't know if that matters.
Oh, there's more numbers after this?
There's like 5.728571429.
Oh, wait, you wanted the whole thing? I rounded it up.
Yeah,
Yeah, something like that.
okay. So 5.7,
728571429.
I think there's another issue, but, okay, that. All right, so make the math trickier, so 6, 2, 8, 5, 7, we'll just take it out 5 decimal places. This will be 1.4271. 4. No, I messed up there. Let's see, 7.2. 4. Oh, here we go. 4, 7, 1, 4, 3. Negative 4, 2, 8, 5, 7. Negative 3, 7, 1, 4, 3. Good with. Any errors in there? I'll tell you what, that's gonna make for some exciting video here. If you add them all up, you get 0? Or close enough within rounding?
Negative 0.01428.
Negative 0.01248.
428.
428. Is that close enough? It seems like I've made a mistake somewhere, but anyone, we'll go with what we have here, no one's gonna correct it. We will assume we're spot on. At some point, there was one particular class, I was doing this derivation, whole board was covered, I was over to here and I realized there was a mistake somewhere, because the answer was not what it should have been. And so now I'm trying to figure it out, and the student says, well, you actually made a mistake back there. Yeah, correct my mistakes as soon as possible. All right. So obviously, if we add them all up and then divide by the number of numbers, we're gonna get a really tiny average here. Matter of fact, since they should add up to 0, we should get an average of 0 of these numbers, so that really doesn't help us. So we need to get rid of the negative somehow. Now, the way the statistic people said is that we're gonna square them all. So they square each of these. I'll go ahead and do this one for you. If somebody could just quickly give me the numbers here, if you square them, and just take it to 2 decimal places, or to 2 significant figures. Oh, that still shouldn't be, oh, that's where that should be 2.02857. That'll count for, I like that positive number. I'm gonna go close enough.
So that's 0.40.
The first one,
Yes.
like 7.40? That can't be right. Because it's a number less than, that's 0.6 here. 0.40?
Yep.
Let's take one more.
Well, it would be 0.395.
It would be-
Yeah, it'd be 0.395.
0.395, okay.
Yeah.
I appreciate, and again, I said 2 significant figures, I believe, and that's what he gave me. I'm fickle.
The next one is 2.165.
So 0.184.
Next one is 0.138.
1.62,
Give me one more decimal point.
then 1.616.
616.
617.
Yes, 7.
617.
So this is gonna be 4 point something.
Is that a 9 on the bottom? The last value,
4.1.
Or, it's right here?
the value that we have to square, the last value we have to square.
That's 2.47143. Sorry, what is this one?
4.1.
4.1? Oh,
Yeah.
right.
6.108.
All right, so now we add all these up. We're not finding the average of them in the traditional sense. So we add all the squares up. $14.6 something.
$14.707.
707, all right. Now, the question is, what do we divide by? Because we're trying to get up some sort of average value, and it comes down to what kind of standard deviation we're trying to find. There are basically 2 types. There's the sample, and then there's the population. Are we doing a standard deviation for every single possible measurement?
No.
So we're doing a sample. We took a sampling of, if I can do math correctly, 7. We did sampling of 7. So we are doing the sample population. So our standard deviation is based upon this average value, which is based upon these 7 samples. This is not an average, overall average. This is an average of just these 7 samples. And so we need to hedge our bets a little bit And for the people who've done statistics, that has something to do with degrees of freedom. So we're gonna divide by 1 fewer than however many numbers we have. So we'll divide by 6. If it were the population, if we had all of them, all the possible measurements, which doesn't make sense in science, but it does make sense in some cases. I mean, there are a finite number of cars, so if we're doing a study of the lifespan of cars, it would theoretically be possible. So we divide by 6 and we get sort of a
2.45.
2.45. So that's sort of an average of our squared numbers. And now we take the square root, because don't forget we squared, so we have to sort of undo that. So we take the square root of that.
1.56.
5/6.
How many decimal places do you want?
That's good enough. So our average, we would express our average as 5.73 plus or minus 1.56. This gives us an idea of the spread of it. If the sample population is large enough, then 68.27% of all measurements would be within this amount of our average. So standard deviation, indication of spread of numbers. However, we need to go one more step. Oh, by the way, for those of you who, on your calculator, I don't have a TI, whatever, so I don't know what the code or the command is. From my recollection, for students who've used their TIs, it basically gives you 2 different standard deviation numbers, one's population and one's sample. Pick the bigger of the 2, if you've given a choice of 2. If you're using Excel or open off a spreadsheet, then you use the command stdev, and then the range of numbers in here. All right. Now, when we're dealing with propagation of dramatic pause here, any questions before we talk about the actual uncertainty? Right? So, what I really want to know is, what is the average value? What is my expected value of this table for the length of the table? Well, I have an average right here, but how accurate is that? So far, I figured out the spread of my numbers, but statistically speaking, my average should be somewhere around here. And so you take your standard deviation, which I'm going to use a sigma for it, even though I think that's properly the one for population, but it's physics, so who cares? So we use sigma here, and I'm going to divide by the square root of however many numbers I actually used. I had 7 numbers there, so I divide by the square root of 7. Officially, whatever the long number is, divided by square root of 7. I'm just making numbers up here.
And 2.165. That long number, the average number, right? Or what number?
No, the standard deviation.
Okay.
Yeah. Sorry, again, read my mind.
0.592.
592. All right. So the statistics people, the statisticians, the statistics people are making the claim that the actual length of the table is 5.729 plus or minus 0.592. This is the uncertainty. So standard deviation tells us the spread of the numbers uncertainty tells us how uncertain we are of what the actual value is.
This is kind of like the tolerance,
Yeah,
like what we can expect it to be, like it has to be between that tolerance, right?
okay, now I'm gonna go with, depends on what you mean. Say it to me again.
Or like, it'll be, but like the length of the table will be between plus or minus 0.592 from the 5.7 to 9.
Yes, yes. The reason I hesitate on tolerance is I did some work with DuPont, and their tolerance is basically nothing can be outside that range. That the chemical specs are so precise that anything outside that can, ruin something.
Yeah.
Awesome.
So, what exactly are we finding when we take the standard deviation and then divide it by the root of the number of samples,
We are finding the uncertainty
the uncertainty of that?
to a, right now it is to a 68.27% confidence level. We're roughly 68% confident that the actual length of the table is this value plus or minus, somewhere within that range right there. Is there another hand up, Roberto?
Yeah, why here by the square of 7 and why to the right, we just divide by 6 instead of 7?
Oh, over here?
Yeah.
Right, you divide by 6 because we had 7 numbers, and I'm gonna botch the explanation because it gets into the statistics aspect of it. Part of what physicists do is they just trust the math people aren't lying to us. 1 plus 1 does equal 2, I'm feeling confident, but I've never seen the proof. We're dividing by 6 because we got all these numbers based upon the average, which was based upon our original 7 numbers. And so we really, we actually lost a degree of freedom in our selection because these numbers are actually all dependent upon this number, which is dependent upon these numbers. That's why we subtract 1 from it. Or the easy way,
It's in the standard deviation formula.
yeah, use your calculator or open off a spreadsheet. And I know that's probably not a particularly satisfying answer, but yeah, in physics, we just have to use the math that they give us.
Do you know how to do it on the calculator?
I do not.
I can show you.
I use Excel, and I actually use open office spreadsheet. I hate Excel. If you haven't gotten that impression from the videos, I hate Microsoft. And you know about the automatic A, right?
The what?
If you can bring Microsoft stock down to penny stocks before the end of the semester, automatic A. You are not allowed to do anything illegal.
Well,
So far, no one's taking me up on the challenge. Right, any other questions at the moment? All right, now the even more fun part. We'll stick with that number right there. So we have our table, and this is 5.729 plus or minus 0.592 meters. Let's give it units. It's a really long table. And we'll say that we've done another set of measurements, and we came out with 3.168 plus or minus 0.129 meters. So that is my length, and that is my width. So each of these has an uncertainty built into it. So my area better have an uncertainty also. So the question is, how do we deal with that uncertainty? Well, I know that area is length times width. And so when I multiply these, I'm multiplying 5.729 plus or minus 0.592 times 3.168 plus or minus 0.129. They are independent, and that is a critical piece right there. These are independent of each other. This number right here has nothing to do with that number other than they're part of the same table. But these calculations were completely independent of these calculations.
So there can be four different options for the number.
No, the statistics people came up with a single option.
Okay.
So first off, you multiply the straight up two averages right there. That's the easy part. So let's just go ahead, somebody, it's somewhere between 15 and 24.
$18.14.
All right. Now we are going to figure out what is the uncertainty in this. The uncertainty is this is when we get into adding in quadrature. So there's two sets of rules for when you're independent. So if you're multiplying or dividing, and you have A plus or minus the uncertainty in A, times B plus or minus the uncertainty in B, then it's A times B plus or minus A times B times the square root of the relative uncertainties added in quadrature. Now, first off, recognize that when I multiply two numbers together, they do not have to be the same units. Perfectly legitimate to multiply two things not in the same units. And so one thing that this does is it makes these terms unitless. But then we have to get it back into the original units. From a unit point of view, we have this unitless bit right here that we're adding in quadrature. And that's the word I keep saying, quadrature. And then you multiply it times the actual product of the two main numbers. And so over here, this would be 18.15 times the square root of 0.592 over 5.729 squared plus 0.129 over 3.168 squared. Someone will reveal this beautiful answer.
$18.15 plus or minus 2.01, 2.02.
What'd you get over here for this?
2.02.
2.02. From a vocabulary point of view, this ratio right here is known as the relative uncertainty. And this number out here, this is the absolute uncertainty. So multiplication and division, you add the relative uncertainties in quadrature and then multiply times the main product or main quotient. Questions to hear? Suppose instead of multiplying, we want to divide them for who knows whatever reason. Oh, actually, I jumped ahead a bit. There is one mistake with our final answer there.
Square meter, no meters.
What would, okay, no meters, but it's, don't forget meters times meters, so it's meter squared.
Squared.
Either put parentheses around it and put meter squared down after it, or distribute and have meter squared after each number. Don't just stick it after the last number without parentheses. All right, so if I wanted to divide them for some reason, length divided by width, then 5.729 plus or minus 0.592 meters divided by 3.168 plus minus 0.129 meters. We have our main number right here, just the two averages, the division, the easy part, the part that they teach you in math class. So that would be something plus or minus, again, whatever that is, times, and the quadrature part is the same. The 0.592 over 5.729 squared plus 0.129 over 3.168 squared. This will look better. What is the division? What's this part? 1 point?
808.
And we end up with a final answer of 1.808 plus or minus 0.2 something.
.022. 0.022.
0.022?
You use the same equation, just the square root is the same?
Yes. The difference is that number up front. 0.022,
I got a different answer.
what you have?
I got 0.200,
That would make more sense. Unless there's a mistake over here.
Probably.
because I did the same equation as I did up there.
You have 0.200. Anyone else get either of the answers?
I got that.
You had 0.200. It's roughly.
Can you get 0.2008?
Yeah, 0.208, so 0.201 then.
Yeah.
Right, still get the same thing, Mario?
I think I'm doing more math wrong.
No. I'm trying to think if you were doing the square root.
Oh, no,
Ah, okay.
I was just squaring it, but no square root to cancel it out. Because,
Yeah, so the lesson I'm taking away from that is make sure you show your work. It's usually not an issue. 251 students are great about showing work. I had one student who, on every lab, would always hand in like 10 extra pages showing every single bit of his work. If you do your work in a spreadsheet, Excel, OpenOffice, Libra, Google Sheets I'm not as fond of, feel free to email me supplemental work. And that if I need to look at it, I will. If I don't need to look at it, I don't have to. All right, this is a good time to take a break before we talk about addition and subtraction and things where we are dealing with dependent numbers. Stretch your legs. Enjoy fresh air. But in the room, please keep the mask on, nurse off.
Oh, I'm sorry.
Thank you. For those just tuning in, that's what we did. Questions before we talk about something else like quiz?
you're gonna ask them who took calculus, or who's taking calculus.
Thank you. Who is in the Calc 2 right now?
What?
Calculus 2. Was that 152? No, one.
270.
270.
One of those numbers. Math 272 right now. So that was,
I am in 63 in calculus 3.
you're in Calc 3. All right, so who else is in Calc 3? And who is past that? Anyone past it?
I just saw all that 40-something years ago. I'm just trying to remember because I changed the profession a long time ago.
Ah,
Then trying to remember everything.
well, fortunately, the math hasn't changed.
But I jumped to philosophy and biology. Then I haven't used this part in very many years.
Well, presumably, as you get more into the refresh your memory on the calculus and get into physics, the endorphins will kick in and it'll just be a nonstop joyride. Hi, my name is George. I've solved one physics problem in the past 6 months. All right, so let's talk about quizzes. In Blackboard, I think it's cleverly labeled assignments. If you click on assignments, there are various types of documents. Usually they'll be by chapter, and you tend to see there'll be homework or HW, can't remember which abbreviation I used, and then there'll be something that says master set. There's not a master set for every chapter. I don't think there's a master set for chapter 1. I think chapter 2 is the first one that pops in. The ones that are homework, those are textbook problems. As in, they specifically list problems from the textbook. The book solutions are posted in there. I did a cut and paste from what the publisher sent me for the problems that I have assigned you. A couple years ago, I basically through a survey with the students, I said, how many is a sufficient, what is a reasonable number of problems that you should be able to know how to do every week, or for each chapter? And 7 was the consensus, and so that's why there should be 7 problems where you actually have to go out and do math. 7 problems for each of the chapters. For the homework quiz, what I will call the homework quiz, I will take 2 of those questions, change the numbers, that will be the quiz. You will have 20 minutes to do the quiz. So if you like to come in cold to do the quiz, I wouldn't recommend it. In the past, I have sort of allowed almost unlimited time and find some people spending over an hour working on these 2 problems, which they should have seen already. I am going to put a time limit this semester. And if that is an incredibly failed experiment, then we'll adjust, but we're going to try it out. So you should be able to work through the problems ahead of time. The solutions are there. Recommendation is try to work the problems without looking at the solutions first. Sometimes I will give the problems without the solutions, and there'll be another document with the solutions, just because I've had some students in the past who are too tempted by the solutions sitting there, and they wanted to bring up a document that just had the problem numbers without the solutions. So I think I do that for a couple of chapters, but not all of them. So homework quiz will be based upon the book problems. Master set is something that you will do and hand in to me. So that is something I will grade separately. It will count as a quiz grade. Master set problems you get help with someone. My recommendation is if you're working with someone in the class, and it's not wrong to do that. But one thing I find is that some people, it becomes blatantly obvious that someone just copied. Bad memories right now. It was an incredibly stupid error that I saw on way too many homework problems. It was so blatantly wrong. And so the clear indication was somebody did it, everyone else copied, who were part of that. If I see situations like that, I'm not going to play the game of, well, I suspect this person did it and that person copied. I'm not playing that game. It's just, it's wrong, no credit, no partial credit. Yeah, that's it for the threatening piece of this. So I have no problem with the master sets. If you work with somebody, work with a tutor, find other resources, feel free to get help on that. The master set problems come from old tests. So this is it's sort of like forced studying. Because ultimately when the tests come around, someone says, if I know how to do the homework problems, should I do okay? Well, if you know how to do the homework problems, not that you just can do them, but you actually understand them, yeah, you should be fine. But if you want to know what the tests are like, I have old tests posted also. Some with solutions. Some with just answers. There is some stuff from chapter 1 that I did not cover, but I am going to work under the assumption that you can pick some of that stuff up. It's like doing conversions. You did it in chemistry, you've done it in math. The conversions. If this were 110, then yes, I would go over it. 251, it's usually just 1 or 2 people who might have be a little bit rusty. So what I like to do is, usually I'd like there to be at least one class between when I officially say I'm done talking about that chapter and having the quiz, so that you have a chance to ask questions next week. So let's say that September 1st, we'll do the quiz on chapter 1. So if you have questions, you can ask, well, you can send me emails also. You can ask me questions on Thursday, but I'm assuming next Tuesday will be questions. And again, it'll be 2 questions. Numbers are changed from the textbook. Awesome.
So we just covered all of chapter one.
All that I wanted to do right now. I mean, I'm hoping that you can pick up on the pieces that, for chapter one, that I did not cover. Look at the homework problems and you'll go, oh, wait a second, I really need a refresher on this. Or, yeah, I can do this in my sleep. There are certain assumptions I am making based on the fact that all of you have, or in Calc 2 or later. They might be false assumptions. I'm assuming that all of you know trig. And history tells me that's generally true, but there are occasionally people who really had weak math courses in trig. All right, let's actually talk about something that this doesn't really show up in any other course. It actually does show up in calculus, but chemistry people don't talk about it because they don't want you to know. Somebody describe how to get to the water fountain. Give me instructions about how to get to the water fountain. Pardon?
I don't even know where it's at. Water fountain?
Water fountain.
I saw one, go through those doors, then go down the hallway and slightly to the left, and it's on the corner.
Any particular hallway?
Hallway to the left.
All the way to the left.
My left.
Okay.
Through the doors.
What did he just establish there?
Directly inward.
I heard several voices at once.
Field of view, I guess.
Say it
The
again?
field of view.
Is it view?
Yeah,
What do we call that in math?
the window.
Oh. What do I call that in math? We have different math teachers. I don't know what your math teacher calls it.
I don't know, point of reference and coordinates.
Yeah, I was going for a coordinate system. All right, so you establish a coordinate system based upon U. All right. Way to make the universe center around you. I say if the world did not revolve around me, why did my parents call me son? All right, anyway. Yeah, it's old. All right, so so go to your left.
So
I just rotate?
I'm
Right.
not quite sure what you're asking.
You're giving me instructions about how to get to the water fountain.
So from my point of view, I would go through that door on my left, and then I would take the left and then take a right down the hallway, and then the water fountain is on the left. I don't know.
So just go down and eventually it appears?
Yeah.
Anyone want to give something more precise than just down the hallway and it appears?
I know where a different one is. If you turn and face the door and then walk out the door and you'll take a right and you walk down right before.
At what point do I take a right?
Well, once you're out the door, you walk out the door and then you'll take your turn to the right.
So I walk right out the door and take a right.
Yeah, you'll walk out the door, you'll turn.
Trying to kill me?
So,
Yes, it makes sense.
You have to specify how many steps or how many meters and.
Ah, thank you.
so when you know velocity, you have to have a speed and direction, and when you're giving directions in physics, you have to have a coordinate system, and so there's a frame of reference, right?
All right, we're basically summing it up right there. Okay. There are things other than just, somewhere in that direction. We are dealing with numbers in this class. This is not conceptual physics. We do need to have something a little bit better. So direction matters because there is a difference between going right or going left in terms of physical movement. How many have had physics before? Oh. fewer than usual. Is that a half or just shy? Dang it. I had names earlier today. Precious. You've had a physics course before?
Yeah,
Okay.
but not here.
Not here, okay. High school, college? On your own?
It's
Oh, well,
like
yeah,
A
high school.
levels.
Okay.
Yeah.
I had one in high school, but,
You don't want to count that?
I mean, that was 8 years ago for me now, so.
Okay. Oh, so, Roberto's about to give you the evil eye on that one. All right, so when we're describing motion, there are often times where direction matters. There are times where direction doesn't matter. If you get pulled over for speeding, I don't think anyone's gotten a speeding ticket for traveling over the speed limit east versus west. Well, if you've been going west, it would have been okay, but you're going east, so no, I'm giving you a ticket. So there are times where direction matters and times where direction does not matter. And also magnitude matters. It does matter how far I actually travel in that direction. In case of the police, it doesn't matter how fast you are going. So speed, direction, and magnitude matter. Then we are dealing with vectors. We will deal with vectors a great deal. If the magnitude matters and direction does not, like speeding, what's the vocab word?
Scalar.
The math is a little bit different between the two. There's definitely a lot of overlap, but scalar math is the math you've been doing since you started adding. 1 + 1 = 2 is scalar math. The number of people in this room, there's 13 people in this room, that's scalar math. Now, if we're dealing with a vector versus a scalar, there's certain notations that you need to become familiar with. So if I have some vector A, if I'm using a word processing program, this is basically the way it's going to look. They'll have an arrow over top of it. This arrow does not indicate anything to the right, it just indicates that we're dealing with a vector. The arrow always points to the right when you're talking about the symbol here. In class, I do what I call the half arrow, just because it's easier to write. If you're using OpenOffice equation editor, this is what it'll give you. Microsoft, well, you have the option of both depending upon how much time you want to spend looking for it. Sometimes the double print is used for vectors. I actually use double print in one case. When I talk about resultants, I will use the double print R. And then the other one that some textbooks will use, and some websites will use, they'll use boldface. It's too much of a nuisance in class if I'm writing quickly. If I want to talk about the magnitude of a vector, then we add an additional, we can symbolize that by, if I want the magnitude of A, I could write it as just A without the vector symbol over it. Properly, I should do absolute value sign around it, at least. And then some textbooks differentiate between magnitude of a vector and absolute value by instead doing sort of the double absolute value. So all of these would represent the magnitude. Now there's no special symbol that I've seen used for direction, so if I want just the direction, I will just put DIR in front of it, and that's for direction. Questions to hear? All right. Everyone's favorite part of any chapter, vocabulary. Now, there are certain keywords that automatically should trigger in your head, oh, that's a scalar. Oh, that's a vector. So we'll talk about for the chapter 2 and chapter 4, and chapter 3 through example. Position is a vector term. So if I ask for the position of something, I'm expecting the magnitude and a direction. The symbols used for position, I tend to use X. Y also works, Z works. Sometimes people are just stuck in the X if it's horizontal, Y if it's vertical, Z if it's going out. But, you know, X, Y, and Z, whatever you pick for your coordinate system. R is used generally when you're talking about radial directions, like there's some central point and you're talking about moving away or towards it. And then a lot of textbooks will use a generic S. Why S? Trivia time. From where does S come when talking about position? Okay. We'll let that be a mystery. There is no real scale or analog for that, so I'll leave that blank for right now. Displacement. Displacement is a vector term. Displacement is the change in position. We represent change by a capital delta. So delta X, delta Y, and so on. Just a capital delta in front of it. This is change in position. So for example, if I have a coordinate system here, actually I don't want to label the axes, and I start out at some particular point right here, my coordinate system is defining where 0 is. That would be my initial position right there. I got the symbol for position with a subscript I here. I move to this point over here. We'll go for the stunning visual effects there. Yes. I now have a final position. Again, position is where a person is based upon a coordinate system. I'll write this down in just a second. So X of F. So I have some initial position, some final position, but my displacement deals with the change in position. We can sum this up a little bit better. Position, where an object is with respect to the origin. That's position. Displacement is the change in position or where an object is with respect to the starting point. And I do need to differentiate two different ways of looking at that. So give people a chance to write down before I talk about that. So here we go. Take a note of my current position. What is my displacement? Why?
Huh?
Why? Why is it from there to here?
From my point of view, that's my favorite vector. That's the second vector. What joins it is the displacement vector.
All right, so you're assuming that's my starting point over there.
You just say that, no?
Why is that my starting point?
Cause you started moving through there?
But couldn't right here have been my starting point?
Okay.
What's the starting point? Not necessarily. Yeah, if we were describing our current location, we can give longitude and latitude, in which case, yeah, I've never been anywhere near the 0, 0. So what I wanted to do here, and typically the answer that you gave, Roberto, is the one I was looking for, but I want to emphasize here that we do have sort of two different types of displacement. There's overall displacement, in which case my starting point was here and then went to there. Or you could go extreme. Boynton Beach, Florida is my starting point, and then I ended up here. And then there's instantaneous. Now, where was I a moment just before? Now, if I just say displacement, as I did in this case, this should be understood as the one I actually wanted, which was the answer that I was given. So if I just say, what's the displacement? I mean overall. If I want instantaneous, I'm talking about, I need to specify that.
The X, I don't know, that figure of yours over there, which should not be like, yeah, like S initial, S final, and like that we can make a delta X and a delta Y, and that your delta X there will be delta S with your original notation.
Oh, yeah, I took the original notation off for a reason.
Okay.
Yeah, because this X is for position, I don't want it to refer to an axis. Did I miss, I addressed at least one point that you made. Did I miss something?
No.
Okay. All right. There is a scalar analog for displacement. It is known as distance. So if I ask what's the distance traveled, I'm looking for a scalar. If I'm asking for displacement, implied overall displacement, I'm asking for a vector. So I was here, I walked over there, and then I came back. What's my overall displacement, or what's my displacement from here to there and back?
2x, whatever your distance was.
That's the distinction I'm trying to get here.
What's the distance?
Ultimately, I'm back where I started. So my displacement is indeed 0. The distance traveled, however, is not 0, because I did actually travel someplace and back. If you die where you were born, your displacement for your life, 0. All right, so, well, that's distinguishing the two there. The symbol for distance is just that without the vector symbols, delta x, delta y. And this is where we got to be tricky. When I talked about, if I wanted the magnitude, one way of looking at it is just dropping the vector symbol. Well, the magnitude of the displacement is not necessarily the distance traveled. I went from here to there and back. The magnitude of my displacement, 0. Distance is not 0. So they are not necessarily the same thing. So properly, just dropping the vector symbol there really can be misleading. And so if I want the magnitude of displacement, I really should put the absolute value symbols around it. If you're looking at a master set question or a test question and you get confused by that, just ask which one I'm put. Just clarify. Questions before we get to the next round? Velocity, as Kyle mentioned earlier. The symbol for velocity, they went really clever on this one. V with the vector symbol. As Kyle also mentioned, it's how fast and what direction, or speed and direction. Traveling 50 miles per hour north is a velocity. Traveling 50 miles per hour is not. That's speed. The symbol for speed, just V without the vector symbol. It is not S. Mathematically, velocity, well, let's break it down into two types. There's instantaneous velocity, in which case that is dx dt. It is the time derivative of position, or using dot notation, x vector dot. In my experience, the dot over it is automatically a derivative with respect to time. And then average velocity is just the change in position over change in time, or displacement divided by however long it took to do it. And so speed would be instantaneous, would be dx dt, and then average is distance over time. Now, with displacement, when I just said displacement, overall is implied. With velocity, if I just say velocity, instantaneous is. So the default here is instantaneous. If I want average, I need to specify average. And spell it correctly sometimes. And the same will be true for the next one, acceleration, but we'll get to that in a second. Questions before I talk about how I'm just as fast as Usain Bolt? And you can too. You don't believe me?
No.
That's why you have to set up the race correctly. Usain Bolt and I are racing around the track, once around. Usain Bolt goes around in about 40 seconds. It takes me, let's be realistic here, 200 seconds. Yep, that won't work. Let's figure out our average velocities. Average velocity is just displacement divided by time. So when Usain Bolt gets back to the starting point, what's his displacement? Over 40 seconds, that's 0 meters over 40 seconds, so his average velocity is 0 meters per second. I get to the starting point. This is Usain Bolt, and this is me. What's my displacement?
0 over 200. So 0 meters per second.
I'm just as fast as Usain Bolt. Now, from a notation point of view, this is a vector over here. It should be a vector over here. So how do you deal with the direction of 0? Well, the way you get around that is you just put a vector symbol over the 0. It's called a 0 vector. So the magnitude is 0 and the direction is, I really don't care, but it has one. Make up a number, make up a direction if you want to. Now, matter of fact, when Usain Bolt gets there, I'm somewhere around here. Who has a greater magnitude of average velocity? I'm faster than Usain Bolt. So it's all about setting it up correctly. We are not comparing speeds, that would be silly. Yeah, we got time to do this next level. Acceleration. A, with a vector symbol over it. There is a scalar analog for acceleration. It is called acceleration. And it's A without the vector symbol. So, you are taking a quiz or test and it asks for, or a homework problem, and it asks you to find the acceleration, and it does not specify which one are you supposed to find.
The vector?
Most likely the vector one. There are times when it's the scalar one and you're just supposed to know. On a quiz or test, I'm trying desperately to put, when I ask for acceleration, that either with the vector symbol or A without the vector symbol, just so it's clear. If I do not do that, because sometimes, you know what, I just forget sometimes. Especially on the older tests, I didn't do that at that point, and I just expected people to know which one I wanted. So I just ask on a quiz or test. The definition of acceleration. The instantaneous is dv dt. That's for instantaneous acceleration. Or average would be delta v over delta t. And if I just ask for acceleration, instantaneous is supposed to be the default. Although we'll deal with a number of problems where acceleration is constant, in which case average and instantaneous are the same. And now for some trivia. So I have position. Change in position over change in time. It's calculus based, come on. dx dt is velocity. dv dt is acceleration. The acceleration dt is you're in a car sitting at a stoplight, your foot is on the brake. The light changes to green, you slam your foot onto the gas pedal. So you're sitting right here, your back, the headrest, your head's not against the headrest, sitting right here, suddenly you slam your foot on the gas pedal, what does your head do? If you do it fast enough, what would be the verb that we would use?
Jerk.
There we go. This is called jerk. There are other terms that are used. Jerk is basically the US, is the American word for it. Probably any physicist, not probably, any physicist in the US, if you talked about the jerk of a situation within context, they would know exactly what you're talking about. The change in jerk with respect to time. Well, think about that. You slam your foot on the gas pedal, so your head jerks backwards, but suddenly you realize the car in front of you was not going. So you have to slam your foot on the brake pedal. So what your head does is that.
Goes forward.
Pardon?
It goes forward.
So it moves forward. Looking for something a little bit,
Like a word.
yeah, a single word.
Torque.
Toss.
Snap.
Oh, we just set it back there?
Snap.
Snap.
Snap.